So, uh, a very good morning to my professor, Arijit Mandal sir, and all my respective TAs. I am Abhyudaya Yadav, roll number 2511 AI04, and today I am here to present my presentation on the topic of Monte Carlo tree search. So, Monte Carlo tree search is an algorithm used for decision making in the complex environments. So, like we can see that in today's day-to-day life, we face certain challenges where we have to take n number of decisions which are very large. So, to reduce those complexity of such algorithms, we have came towards a solution whose Monte Carlo solution. The algorithm gained global recognition when it was artificial system capable of playing complex games like Go at superhuman levels. So, at Monte Carlo tree search combines two fundamental ideas. The first one is a tree search, which represent possible future decisions in the form of a tree structure. The second one is sampling Monte Carlo simulation, which means using repeated random sampling to estimate outcomes. By combining these two techniques, MCTS can explore possible decision and gradually improve its estimate of which actions are most promising. Okay, so on this, what the central challenges that this MCTS solve? The main dilemma that it mainly solve is exploration exploitation problem. So, what is exploration? Exploration refers to the new actions that have not been tested much yet, while exploitation refers to choosing those actions that already appear to be successful. A good decision-making algorithm must balance these two aspects, and Monte Carlo research is one of them. So, to address these kind of challenges, by using statistical information collected from simulation and guide its research process. This algorithm operates by building a search tree incrementally. Instead of constructing the entire tree at once, it gradually increases its number of levels. Like MCTS gradually expands the trees as more simulations are performed. Over time, it focuses more attention on promising branches of the tree while ignoring less promising ones. So, each iteration of the Monte Carlo search algorithm mainly consists of the four phases. The first is selection, the second one is expansion, third one is simulation, and the fourth one is backpropagation. These all algorithms they create a kind of loop and a cycle of the algorithm, and the cycle is repeated until we the computational budget such as time or the number of simulation gets exhausted. Okay, so let's see what is the first phase of our selection. So in this algorithmic phase, we start with the root node of the tree, which represent the current state of the problem. From there, it repeatedly selects child nodes based on selection policy until it reaches a node that has not been fully explored. The purpose of this to identify most promising path through the tree according to the statistical information collected so far. Now, coming to our second phase, the second phase is called as expansion. When the algorithm reaches a node that represents a state that has not yet fully explored, it adds one or more child nodes to the tree. Each child node corresponds to the possible action that can be taken from the current state. In this way, the search tree gradually grows and represents the maximum possible decision sequence. Now, let's move on to the third phase. The third phase is called as simulation, which often sometimes called as rollout. So, in this step, the algorithm performs a random simulation starting from the newly added node until it reaches a terminal state of the problem. For example, in a game scenario, the simulation continues until the game ends with a win, loss, or draw. The result of the simulation provides an estimate of how good the particular sequence of actions might be. Now, let's come to the final phase, which is also known as the backpropagation. In this stage, the outcome of the simulation is propagated back through the nodes that were visited during the selection phase. The algorithm updates statistical information such as the number of visits and the average reward of each node along with their paths. These statistical information will then influence future selections and allowing the algorithm to gradually become more focused and giving us better results. So, uh, now coming to the what is the key component of this entire selection process? So the key component of this entire selection process, it is in the mathematical form and it is also known as the upper confidence bound or also known as UCT, which is applied to the trees. This formula helps us determine which child node should be selected during traversal. It mainly balances two factors, the estimated reward of the node and the number of times the node has been explored. Nodes with higher rewards are preferred, but the nodes that have been visited fewer times are also explored to avoid the missing potentially better options. Okay, so let's come to our next strength of this Monte Carlo algorithm. So the next main strength of this algorithm is basically called adaptive learning process. Initially, the algorithm performs many random simulation and its estimates are rough. However, as the number of iterations increases, the statistics collected become more reliable. Consequently, the algorithm becomes increasingly confident about which action is the best one to choose. Okay, so there is another important property of this R algorithm, which is also known as the anytime algorithm. So this means the algorithm can be stopped at any moment and still produce a reasonable decision based on the simulation we have performed so far. If the more time is available, the algorithm simply continues running more simulation and improves its estimates further. Okay. So let's explore a brief history about this Monte Carlo algorithm or Monte Carlo search trees. So basically, what happened that historically the main version or the basic version of the Monte Carlo search tree was introduced around 2000 in the year 2006 and quickly became one of the most influential algorithms in the game playing artificial intelligence. Over time, researchers have proposed numerous improvement and extensions to enhance its performance in different environments. So, just by saying that it enhances its performance in different areas, like things may not be that much clear. So, let's focus on one major research areas. So, the this research mainly focus on the reducing the branching factor, which refers to the number of possible actions available at each state. In many complex problems, the number of actions can be extremely large, which makes the search space grow exponentially. Researchers have developed techniques such as action pruning, historic filtering, and macro actions to reduce the number of actions considered during the search. Okay, so we have seen whatever we have seen so far. Let's deep dive in some more of its what improvement this algorithm provides us. So there is another area of improvement deal with imperfect information environment. In some problem, the algorithm does not have to complete knowledge of the current state. For example, in card games or real-time strategy games, some of the information may be hidden from the player. To handle such scenarios, modified version of MCTS have been developed, including methods like perfect information, Monte Carlos, and the information set Monte Carlo tree search. Now, Monte Carlo tree search has been successfully integrated with many other machine learning techniques. In the hybrid systems, machine learning models help guide the search process by estimating the value of states or suggesting promising actions. A well-known example is the combination of neural networks with MCTS in modern game playing systems. Okay, so at this point, we have only explored in the field of games. So, what happened if we have to apply this algorithms in a real world domains? So, MCTS applications in the variety of real world domains as well. In robotics, it is used for planning sequences of actions that a robot should perform in uncertain environments. Like, suppose what happened if certain conditions happen in front of that robot, which is not been earlier programmed. Okay, so in transportation and logistics, it helps solve vehicle routing and scheduling problems where many alternative routing must be evaluated. In security planning, the algorithm can assist in determining optimal patrol strategies in adversarial scenarios. It has even been applied in areas such as chemical synthesis planning, where researchers use it to explore possible sequences of chemical reactions. So these are the kind of scenarios where MCTS it has to perform its algorithm on its own. Like these kind of thing you cannot just randomly provide to these are the very random occurrence of events. Okay, so MCTS quite impressively perform all this task. So despite its many strengths, Monte Carlo tree search also has certain limitations. So one major limitation is the explosion of the search space in problems with extremely large number of possible states. In such situations, the algorithm may require a very large number of simulations to provide reliable results. Researchers addresses this issue through techniques such as hierarchical search, state abstraction, and parallel computing. Okay. So, like till now, we have seen only few challenges. Let's explore one more major challenge involved with the quality simulations performed during rollout phase. If simulations are purely random, they may not accurately reflect realistic strategies, especially in complex environments. Therefore, many modern implementations incorporate domain knowledge or learned policies to improve the quality of the simulations. Okay, so like we have discussed everything about the MCTS, but we have discussed about its drawback from where what real world role this algorithm play. Here I am going to present one more advantage of this MCTS is that it's highly parallelizable. Different simulations can be executed simultaneously on multiple processor or computing nodes. This allows the algorithm to scale efficiently when more computational resources are available. Okay. Like whatever I have explained earlier, that it's support high parallelizable. Different simulation can be executed. These kind of things when happen when we highly make our algorithm highly parallelizable. So what happened that it reduces the efficient time of the entire complex problem that we are facing, and it also make the decisions very quicker than other possible algorithms that are present. So, if I have to give a summary of this entire whatever that I have presented in front of you, so Monte Carlo research represent a very powerful framework for solving complex decision-making problems. By combining the tree search with statistical simulation, it provides effective way to explore enormous search space while gradually improving decision quality. Okay, the algorithm four-phase cycle, selection, expansion, simulation, and back propagation enables it to learn from repeated trials and refine its strategy over time. The versatility of the MCTS has made it one of the most influential algorithms in artificial intelligence research. Over the past 2 decades, from board games to robotics, logistics, security planning, and scientific discovery, it continues to play an important role in solving problems that involve sequential decision making under uncertainty. To conclude, Monte Carlo research demonstrate how probabilistic reasoning and iterative simulations can transform complex decision programs into manageable computational process. Its ability to adapt, learn from experience, and improve with additional computation makes it an essential tool in modern artificial intelligence. Okay, so that is for all whatever I have presented in front of you about the MCTS. Uh, uh, by this presentation, even I have learned a lot of about this Monte Carlo research. I have for making this presentation in front of you. I have referred to the mainly two research papers which were provided by our respective faculty, Arijit Mandal sir. And I'm very glad that I'm able to explore such a complex topic in such a easy way through all those research material. So that's it from my side. Thank you.